So vacuously true statements are quite useful, and they especially are useful to deal with empty sets, so, or rather an empty set. So what is an empty set? An empty set is a set with no elements. Okay, so now you can you are allowed to be confused with this definition, because how can there be a set with no element? And it is similar to the question of the number 0, and many people were confused when the number 0 appeared in mathematical literature, because they said, how can something be nothing? Okay, and how to interpret this statement? We always think of it as a convention. Okay, so an empty set is a convention. What do I mean by convention? It's an agreed upon rule. And with this convention, many things become easy. For example, we saw that in the definition of the intersection of two sets A and B, we wrote X such that X belongs to A and X belongs to B. But we know that there can be sets for which these statements may not hold at all, right? So in that case, so if there are no elements X for which X belongs to A and X belongs to B, then A and B are called disjoint sets, and we write A intersection B as this symbol phi, and this symbol stands for the empty set. Okay, so here we see that no element X satisfies the condition that X belongs to A and X belongs to B simultaneously, so it is the empty set. So this is by convention, and with this convention, it is true that it holds that phi is a subset of every set. Okay, let's call it A. So for any given set, this empty set will always be a subset. Why? So remember that the definition of a subset was that, so A is a subset of B, A is a subset of B if all elements of A are also elements of B, right? But in this case, if you take the statement phi is a subset of A, then we say that for all elements in the empty set, so all elements in the empty set, let me write this way, all elements in the empty set also belong to A. But the empty set is empty, it has no elements, and so the first part, so this part P, so you can also write it in terms of an if-then statement. If you put this as Q, then you can rewrite this as that if an element belongs to the empty set, then it belongs to A. So here now, this part is your P and this part is your Q, and I've just rewritten these are both mean the same thing, but I've rewritten it in terms of an if-then statement. And now note that P never holds. P is never true because the empty set does not have any elements. Okay, is never true. So this statement is vacuously true. So in this way, phi is a subset of A, always holds for any set, for any set A. Now let us look at a couple of set theoretic properties of the empty set. Set theoretic properties. The first is that A union with the empty set is always the set A, and the second is that A intersection with the empty set is always the empty set. Okay, so with the definitions of the union and intersection, try to show these using if-then statements. Okay, and so you will understand where the vacuously true statements play a role in proving these things. Okay, now for this if-then statement, if P then Q, we write it as a notation. We write it as P with this double arrow, and we read it as P implies Q. So this is a shorthand notation for an if-then statement, and for an if-then statement there are three possible constructs. One is the contrapositive, then there is the converse, and then there is the negation. Strictly speaking, these two are for if-then statements, and this is for any statement. Okay, so let's try to understand what is a contrapositive and a converse for an if-then statement. So a contrapositive statement of a statement P implies Q is given by the statement not Q implies not P, and by not Q I mean not Q is the negation of Q, and this is the negation here, negation of Q, meaning that when Q is false, when Q is true, then not Q is false, and when Q is false, then not Q is true. So it's just the logical opposite of the statement Q. So similarly, not Q is the logical opposite of the statement P, and the negation is just it just means this logical opposite statement. And the contrapositive of the statement P implies Q, of the statement P implies Q, is this statement not Q implies not P. And the contrapositive and the statement itself, they are both logically equivalent. So P implies Q is logically equivalent to its contrapositive not Q implies not P, meaning that when this is true, this must also be true, and when this is false, this must also be false. So you can write it as a pair of if-then statements. So it means that if P implies Q, now here this is a statement in itself, and let me write it with a capital P like this, then not Q implies not P, and this is our capital Q, and here we can write P implies Q like this. So it means that whenever P implies Q is true, then not Q implies not Q is not P is true, and similarly if not Q implies not P is true, here this is our Q, then P implies Q, then this is our P. So here Q also implies P. So when P implies Q and Q implies P, then we write P is equivalent to Q, and we use this two directional double arrow to write that they are logically equivalent. Logical equivalent just means that whenever the first part is true, then the second part is also true, and when it is false, then this is also false. So this is the contrapositive statement. Now what is the converse? Converse of P implies Q is the statement Q implies P. So you are just reversing the roles of P and Q here, and of course if this is true, then the converse may not be, well, it may be true or false. Okay, so we cannot say that one implies the other, so this may be true or false. Okay, so these are the logical constructions that we use all the time in mathematics. And now let me say a few words about a mathematical proof, what it means and how we use it in logic. So a mathematical proof, so first let me introduce this terminology. So in the statement P implies Q, P is called the hypothesis, and Q is called the conclusion. Okay, so this is some terminology, and with this terminology we can write what a mathematical proof is. A mathematical proof is a statement P implies Q has a mathematical proof if it can be connected, if we have a chain of logical statements whose beginning hypothesis is true, is P, and the end conclusion is Q, and all the logical statements in between are true, are known to be true. okay, in logically. So what it means is that you have statement P here and there's another statement Q here, and then you try to fill out these statements in between. So P1, P2, and so on. Here we have Pn, and lastly you have Q. So all these if then statements, these are known to be true. So true, 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 and then we can infer that this P implies Q is true, and this is basically a mathematical proof, right? So for example, we wrote that if x square is positive, then x to the power 4 is positive. So what is a mathematical proof for this? We say that well, we can, if x square is positive, then x square into x square is greater than x square into 0. Okay, so by the order properties of real numbers, which is that if x is greater than y and z is greater than 0, then x into z is greater than y into z. Okay, so with this, so if you consider this as z, and if you so this is z, this is x, and this is y now in this notation. So I'm using x as twice, but I hope it is clear. So this x is this x here, and so x square times 0 is of course 0, and on the left side we have x to the power 4 is greater than 0. So this is just a small proof where you started with P and you ended up with Q, but here you had another statement P1, right? So and P1 implies Q. So we had P implies P1 implies Q. So this is an example of a mathematical proof. Now let me end by describing what is a proof by contradiction, which we will be using a lot in this course. So a proof by contradiction is a mathematical proof where you start by assuming that a certain statement is true, a certain statement is true, and then deduce by a chain of logical statements, just like a proof, statements that another statement which is known to be true, is false. Okay, so you have to deduce starting from a certain statement, assuming that it is true, and then deduce by a chain of logical statements that another statement which is known, you know it previously, or you deduce it from in another way to be true, and then by this chain of logical statements it becomes false. So since it cannot be true and false simultaneously, because we do not allow such things, as I said earlier, then your original statement must be false, which you assume to be true. Okay, so let me because there's a lot of true and false and going back and forth, maybe it will help if I illustrate this with an example. So I'll take this same statement that I gave a proof for, and I'll prove it by contradiction. So proof by contradiction. So the proof by contradiction is say that this is suppose suppose that this statement is not true. Okay, is not true. So we are assuming that the negation of the statement is true here. Okay, so here I'm saying that assume that that a certain statement is true, but here I'm assuming that it is not true, but it is equivalent to saying that the negation of the statement is true. Okay, so whether you assume it is true or false is the same thing. Now if you assume that this statement is not true, what does it mean? So you have to find the negation of this statement. Negation of this statement, x square greater than 0 implies x to the power 4 greater than 0, and the negation is that there must exist an x naught such that x naught square is greater than 0 but x naught to the power 4 is less than or equal to 0. So this is the negation, and here I'm changing. So this statement x square greater than 0 has for all in hiding. Okay, so for all x square greater than 0, this implies that x to the power 4 greater than 0, and for all gets changed to exists. Okay, so when you take the negation, for all gets changed to there exists. Okay, and similarly if you take there exists, then it gets changed to for all. So now suppose that there exists an x naught for which x naught square is positive but x naught to the power 4 is less than or equal to 0. So how do we get a contradiction? So because x naught to the power 4 is less than or equal to 0 and x naught square is greater than 0, then we can divide, because x naught square is strictly positive, we can divide on both sides. So x naught to the power 4 by x naught square is less than or equal to 0 by x naught square. Okay, again by the order properties of the real numbers. And here you get x naught square. This implies that x naught square is less than or equal to 0, which directly contradicts the fact that x naught square is greater than 0. So if this is true, this cannot be true, and this must be false. But by a chain of logical statements, we have proved that this is true. So since this cannot be true and false at the same time, this means that our original assumption was that there must exist an x naught such that this happens. This must be false, and this implies that for all. So our assumption of the negation of the statement was incorrect. And this means that for all x square greater than 0, we have x to the power 4 greater than 0. So this is an example of a proof by contradiction, and something that we will use many times in this course. So now that we have formed some basis in logic, we will try to understand the relationship of sets with functions.